Okay, so in a previous video, we tackled the issue of a particle in a box surrounded by an infinite potential. So our potential was zero in a certain region of space and infinite everywhere else. And we solved this problem, this exact same problem, in two ways. In the first way, we considered an asymmetric potential relative to the origin of coordinates. So we took our potential to be zero between in the region of 0 to L and infinite elsewhere. And we've came across the solution to the wave function to the Schrodinger equation, and we got these quantized wave functions, which the psi squared represented the probability of finding the particle in a position x. And we have also calculated the energy eigenvalues, which were also quantized and have the following expression of h bar squared divided by 2m multiplied by n pi over L squared, where n varied from 1 to varied over all the integers, so it's 1, 2, 3, and so on. And then we took a second approach to the problem and we solved it in a symmetric potential. Now, in theory, the choice of coordinates shouldn't make a difference in reality, and it doesn't, to what you measure. It doesn't make any difference to the physics of the problem. To have your coordinate system, let's say, at the origin, or to have it, or to shift it by any amount in any given direction, you should always get the same physics. And by physics, I mean you should get the same probabilities and the same energies. So we should get, so if the wave functions that we get, they better have the same, if they're not exactly the same, at least their square modulus must have the same value regardless of the solution that we get. And so it appears that when we did this shift, when we had a symmetric potential that goes from minus L over 2 to L over 2, and it was 0 in that region and infinite elsewhere, our solutions were split into odd and even solutions. So we had two wave functions instead of one. One that went with a cosine function and odd multiples of pi, and it had its own energy eigenvalues, and we had an even solutions where the index was an even number and it was a sine function, and it had its own energy eigenvalues. So it appeared that we've somehow, by just shifting the coordinate system, we've made two different solutions that sort of don't resemble the original one at first glance. However, let's, for example, take into consideration the case where n equal 1 in the asymmetric one. So we'll have psi of 1 x equals the square root of 2 over L sine of pi L over x. So that's the solution, and the corresponding energy to this energy eigenstate is E1, which equals h bar squared over 2m pi over L and all of it squared. So that's the solution that we get from the asymmetric well. Now, suppose we would like to see if there's any corresponding solution on the other side. Now, obviously, 1 is an odd number, so we need to take into consideration the first wave function with its first energy eigenvalue. So for 2n plus 1 to equal 1, n has to equal 0, and we'll have that psi of 1 in this case will be square root 2 over L cosine, and substituting n is equal to 0 in this case, we'll get pi over L x. And for e of 1, we'll get h bar squared over 2m. And again, substitute n is equal to 0 in this equation, we'll get pi over L squared as well. So it appears that even though the indexing, the numbering for the eigenstates and eigenvalues is different, we get the eigenstates appear to be slightly different. So here we have a sine, and in the other solution we have a cosine, but the energy eigenvalues at least are the same. Now, if we examine again, let's say for n is equal to 2, we get that psi 2 of x will also equal the square root 2 over L sine 2 pi over L x, and E2 will equal to h bar squared over 2m 2 pi over L squared. Now, since 2 is an even number, to go to this solution, to the symmetric solution, we need to use the even wave function, and we have that the subscript is 2n, so for in order to get 2, n has to equal 1 in this case, so for n is equal to 1, we get psi of 2 of x will equal to square root 2 over L sine, and guess substitute n is equal to 1, so it's going to be 2 pi over L x, and the energy eigenvalue is h bar squared divided by 2m, and we substitute again, n is equal to 1, we'll get 2 pi over L squared. So in this case, in the even case, the eigenstate agrees, so we have the same solution in both cases. So we have a sine function here and a sine function there, and the energy eigenvalues agree. So in this scenario, we're kind of safe, because even when you square both wave functions, you know the probabilities are going to be the same. But what about the odd case? You have a cosine, you have a sine, it seems a little bit sketchy, but at least the energy eigenvalues remain the same for these cases. But let's plot the functions. The only way to make sure is to plot psi squared as a function of x and see if the two wave functions agree on the solution, if they give us the exact same probabilities in their respective domains. All right, so in order to visualize the solution that we've got, I've gone ahead and written some Python code in a Jupyter notebook. And the first line of code is just importing libraries. And I've defined the original asymmetric wave function that we had, which was a function of sine, as a function psi n, and defined the solution that we got symmetrically as an even function and an odd function. Defined that as well. For simplicity, I took the length of the block to be of unit length, just for presentation purposes. It doesn't change anything in the solution. And defined the respective domains, which are the symmetric that goes from 0 to L, and the other one which goes from minus L over 2 to L over 2. Now I took, in the first case, we took n is equal to 1. So when n is equal to 1, in the asymmetric case, that's an odd number. So in the symmetric case, we'll have to use the odd wave function. And so here I've went over and plotted the wave function, the magnitude of the wave function squared in both cases for n is equal to 1 in the asymmetric case and n is equal to 0 in the symmetric solution for the odd wave functions. And as you can see, that the probability of finding the particle is exactly the same. So the two curves are the same in the asymmetric solution, which is shown in red, and the symmetric solution, which is shown in green. But the only difference is the symmetric solution is shifted to the right by minus L over 2. So it's centered around the origin, while the symmetric solution is centered around half the box, so it's centered around L over 2, while the symmetric solution is centered around the origin, which is to be expected since the wave function is defined in completely two different regions in space in the two coordinate systems. However, the relative probabilities remain the same. Now I went ahead and did the exact same thing with the asymmetric wave function, but for n is equal to 2, which is an even number. So we in this case we'll have to use the even wave function from the symmetric solution with n is equal to 1, and again plotting the magnitudes as a function of position, you would see that the probabilities are exactly the same in the asymmetric solution and the symmetric solution, but they are just shifted relative to the origin by L over 2 in the symmetric case. So the physics remains the same, even though the function in and of itself looks slightly different.